This portion of chapter 2 is going to cover acids and bases. Right here we see examples of naturally occurring acids. This is citric acid, which is found in our citrus fruits. And then in our cleaning reagents, we have compounds that are mostly bases. So we have in Windex, we have ammonia. And then in soaps, we usually have sodium hydroxide. Here are a few more examples of acids and bases. So here we can see acetic acid, which is a common acid in vinegar. We have HCl, which is found in our stomach. And then we have sulfuric acid, which is usually found in car batteries. Now, acids and bases can be classified either as organic or inorganic acids. So what are organic acids and what are inorganic acids? Basically, organic acids contain the element carbon. We've already defined what organic chemistry is. The definition is compounds that contain carbon in their structures. So here in acetic acid, you can see the carbons are on these positions. And then we have another compound which is called benzoic acid. Now if you're doing 3100 lab, you should have already started using benzoic acid, which was one of the compounds you used in experiment 1. So we're going to learn later on how to draw structures of compounds. So here this is a carbon, that's a carbon, and so forth. Inorganic acids, of course, are those that do not contain carbon as part of their structures. So you can see examples include HCl, sulfuric acid, nitric acid, and phosphoric acid. All these do not have carbon in their structure. Organic bases, again, they're bases, but since they're organic, they should contain the carbon element. Whereas inorganic bases, as listed here, they do not contain your carbon atom. Now, acids and bases have been defined in different ways. We have 3 definitions. We have the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis acid definition. Why do we have so many different definitions for acids and bases? The reason is when they first discovered acids and bases, they started with a basic definition of acids and bases. So an acid, in terms of the Arrhenius definition, an Arrhenius acid is a substance that releases hydrogen ions, that is H+, when it's in solution. Whereas an Arrhenius base is a substance that releases hydroxide ions, that is OH- when in solution. So this definition was very limited because it only applied to only those compounds that when they're placed in solution, they would have to release an H+. If it's a base and it's placed in solution, then it should release OH-. But as time went by, they realized that there were other compounds that were not able to release an H+ or an OH-, so they had to broaden the definition. Hence the reason we have the Bronsted-Lowry definition, which again was kind of limited, so that's why they came up with the Lewis definition of acids and bases, which encompasses all kinds of acids. So in terms of the Bronsted-Lowry definition, your acids are basically substances that donate a hydrogen ion, whereas your Bronsted bases accept hydrogen ions. So below is an example of an acid-base reaction, and we're going to use the curved arrow formalism to show the movement of electrons. This curved arrow shows where electrons are moving from and where they're going to. And then you should be able, by the end of this chapter, you're going to be able to know how to use the curved arrow formalism and then to come up with the structures of the products that are formed from an acid-base reaction. So normally, and I want you guys to get this from the start, you always move your arrow from the base to the acid. Again, the arrow always moves from the base to the acid. So we're going to use this arrow. So here, your bases, you can identify bases mainly if you have nitrogen-containing compounds. Generally, they're identified as bases. Or bases can also be identified if a compound contains lone pair of electrons, like we see in this compound here. So we're going to move an arrow from the base to the acid. So remember, acids donate a proton. So it's this proton that's going to be donated to the base, and then the base is going to accept the proton. So if you use the curved arrow formalism, remember it moves from the base to the acid. Okay, so then once you move the arrow here, this bond is going to break to the oxygen. And the reason why you don't just stop by putting the arrow here, remember hydrogen is in group 1. It only forms one bond so that it can become like helium. So if I stop here, it means hydrogen is going to have 2 bonds. So this is why this bond has to break so that these electrons can go to the oxygen. So when that happens, then you can see that the electrons, these electrons here came from this bond here. So the oxygen now gains a negative charge. Nitrogen has used its lone pair of electrons. So then it's electron poor. So then again, if you look at the product here, nitrogen was already attached to 3 hydrogens. So now it has 4 hydrogens. That means it's forming 4 bonds. And remember, nitrogen is only allowed to form 3 bonds. So if it has an abnormal number of bonds, then it has to carry a formal charge. So the plus charge here is due to a formal charge. But one way that you can remember this, what charges do you put where? If you break a bond, the electrons, if they move to an atom, that atom gains a negative charge. If you lose a lone pair of electrons, that atom will gain a positive charge. So this is an acid, this is a base. The compound in your product which contains your negative charge is called the conjugate base. If it contains a plus charge, this is always referred to as a conjugate acid. So you need to know the terms. You need to be able to, if you're given a reaction, you need to be able to identify what is an acid, what's a base, what's a conjugate base, and what's a conjugate acid. There are 2 types of organic acids. The first one is those that lose a proton from an OH, like in these 2 compounds. So you can be able to differentiate between an acid which is weak and which one is strong. The way you do that is if you write an equation such that you move from an acid to a conjugate base, the stability of your conjugate base determines how strong the corresponding acid is. So if you look at these 2 acids, when you lose a proton, when you lose this proton in an acid-base reaction, you get this conjugate base. When you lose this proton here, you get that conjugate base. Now, what's the difference between this conjugate base and these 2 conjugate bases? Here, when you get the conjugate base, you can use the curved arrow formalism to write resonance structures like this and like that. Remember, we just covered resonance structures. So when that happens, then you form a double bond here. This bond, the 2 electrons are lost, so they go to your oxygen. So you have a negative charge here. Now, the main difference between this conjugate base and that conjugate base is this conjugate base, you cannot write resonance structures, whereas for this conjugate base, you can write one other resonance structure. So in other words, this resonance structure is stabilized by resonance and by the very fact that the negative charge is on oxygen. So the more resonance structures a compound is able to form, the more stable the conjugate base, and hence the more stable the corresponding acid. So, but when you're talking about strength of an acid, you always have to look at the conjugate base, and in both cases they contain a negative charge on the more electronegative atom. But this one here is much stronger. In other words, this acid is much stronger because you have 2 resonance structures, and in both cases the negative charge is on the oxygen. The second type of organic acids are those that lose a proton from a CH, and normally this CH3 is closer to a carbonyl functional group. A carbon doubly bonded to an oxygen is called a carbonyl group. So when this CH3 loses 1 proton, then it becomes this compound here. So that means the negative charge is on the CH2. So if you write resonance structures, then you move this pair of electrons to this bond, and then the next electrons from this bond move to the oxygen to get your next resonance structure. So here you can differentiate which one is major and which one is minor. Remember, the major compound usually has the negative charge on the more electronegative atom. This is minor because the negative charge is on the less electronegative atom. So let's move on to organic bases. Organic bases can be identified by either having a lone pair of electrons. So for example, this compound here, you have lone pair of electrons on the oxygen, or they can also carry a negative charge. So for example, this is ethoxide, it has a negative charge. Now, generally nitrogen-containing compounds are usually bases. So for example, this compound here, this is an amine. And then another example is pyridine. It's a benzene ring with a nitrogen element. So this is called pyridine. Now, oxygen-containing compounds can act as either bases or acids. It all depends on what they're reacting with. So we're going to have examples where we can be able to see that oxygen-containing compounds can act either as acids or bases in your next slide. In this slide, I've put examples 1, 2, and 3. I want you to try and put in the arrows. First of all, you have to identify which one is the acid and which one is the base, and then put in the curved arrows, and then try and figure out what the products are in each case. And then we'll discuss this in class. So here are a few more examples of acid-base reactions. So again, I want you to identify which one is the acid, which one is the base, and then use the curved arrow formalism to move the electrons. Remember, the arrow always moves from the base to the acid. And then I want you to predict the products in each case. Now here we're going to concentrate on acid-base strength. So you can talk about strong acids and weak acids. Generally, your strong acids are going to dissociate completely in water, whereas your weak acids usually dissociate partially. So we use this kind of arrows to show that most of the acid has dissociated completely. That means the forward reaction is more than the backward reaction. These are equilibrium arrows. And then if the backward reaction is greater than the forward reaction, then this arrow is longer, this arrow is going to be shorter. So you can also talk about acid strength using the pKa value. Normally a strong acid has a small pKa value, whereas a weak acid has a large pKa value. Here is a question that you can work on based on the information you obtained from the previous slide. So remember that we said there were several definitions of acids and bases. The first was the Arrhenius definition, followed by Bronsted-Lowry definition, and then the Lewis definition. So this slide we're going to concentrate on what a Lewis definition is. So a Lewis acid is defined as an electron acceptor, whereas a Lewis base is an electron donor. But for a Lewis acid to be an acceptor, it means it should have an empty orbital, that is, to be able to accept the electron which is donated by the Lewis base. So how can you identify what's a Lewis base and what's a Lewis acid? Generally, your Lewis bases are also known as nucleophiles. That means they have electrons to donate, whereas your Lewis acids are also known as electrophiles, so abbreviated E+, nucleophile is abbreviated N with the 2 dots. The 2 dots means they have electrons to donate. And examples of Lewis bases include nitrogen and oxygen containing compounds such as these two. And then generally you can be able to tell that a substance is a Lewis base if it has a negative charge or if it has a lone pair of electrons. Now remember, not all compounds that have lone pair electrons are going to act as bases. They can also act as acids. It all depends on what they're reacting with. And you can refer back to the reactions that we've done in previous slides. Now a Lewis acid being an electrophile, that means it's electron poor. It has a plus charge. That means it's able to accept an electron. Examples include group 3 elements such as BF3. So you have an empty orbital here. Aluminum trichloride is another example. This is group 3 elements, aluminum, boron. So this also has an empty orbital. That means it does not have a complete octet. Also, examples include all compounds that carry a positive charge. Positive means they're electron poor, so that means they can accept an electron from a Lewis base. So I've just given 2 examples here. Here are a few questions where, once again, I want you to identify the Lewis acid, the Lewis base, and then use the curved arrow formalism to show the movement of electrons, and then predict their products in each case.